So, welcome back to the lectures on Engineering Mathematics 1, and this is lecture number 26. We will continue the discussion on beta and gamma functions. So, these are the special type of examples for improper integrals, and today we will be talking about mainly their properties and how to evaluate those integrals. And in the last lecture we have already seen the convergence of those integrals, and if we recall that the beta function was this improper integral 0 to 1 and x power m minus 1 1 minus x power n minus 1 dx, which converges when this m and n, these number here in the power exponent here. So, m and n are strictly positive and they diverges, this integral diverges when m and n they are less than or equal to 0. And we have also seen for the gamma function that this integral, this mixed type of improper integral 0 to infinity e power minus x x power n minus 1 dx, it converges if this n is strictly greater than 0 and it diverges when n is less than or equal to 0. First we will discuss the property, one nice property of this beta function, which is the symmetry property, and this is the improper integral for beta b m n, and if we substitute here for 1 minus x is equal to y, then we can easily see that the b m n is equal to b n m. So, let us do it here. So, if we substitute here 1 minus x is equal to y, that means minus this dx is equal to dy, and then this integral. So, then x 0, so y 1, and then we have there 0. So, x power m minus 1. So, from here the x becomes 1 minus y. So, x power m minus 1. So, we have 1 minus y power m minus 1, and 1 minus x is y. So, y power n minus 1, and this dx will become dy with negative sign. So, this we can revert now. So, 0 to 1, and we have y power n minus 1 and 1 minus y power m minus 1 dy. So, this is the again the beta function, and which as per our notation this will be denoted by beta. So, this is here 1 minus, so y power n minus 1. So, this is n, and 1 minus y power m minus 1. So, as per our notation this is beta n m. So, this beta n m is equal to this beta m n. So, we have the symmetry property here. So, it does not matter whether we compute this beta with m n or with beta n m. So, that we will keep in mind now in future discussion. And so, how to evaluate this beta function? The question is the evaluation, because these are the special integrals, improper integrals, and special care has to be taken to evaluate these beta functions. So, suppose here n is a positive number. So, in many cases we can discuss that or we can compute that integral in a very simple fashion. So, first case we are considering here when n is a positive number. So, in this case we consider this beta m n as a given integral, and now if we integrate this by parts and taking that this n is taken as a positive integer. So, we will differentiate this part of the function, and then this will be for the integration when we do this integration by parts. So, this will be here the integral of this x power m minus 1, which is x power m and divided by this m for this x power m minus 1, and now this will remain as it is. So, 1 minus x power n minus 1, and then we have these limits 0 to 1 plus the integral of this x power m minus 1 with the minus sign there, but that will be compensated. So, here x power m divided by m, and then we have n minus 1 and 1 minus x power n minus 2, and the dx. So, this is here n minus 1 and this divided by m. So, we have now what is left. So, n minus 1 and divided by m, we have taken this out of the integral. So, the integral becomes 0 to 1 x power m and 1 minus x power n minus 2, and this is dx here. So, we have integrated by parts the integral, keeping in mind that this n is taken as a positive integer. So, that we will be now differentiating this function wherever needed, and this will be used for the integral. So, we have integrated the function and it is kept as it is in the first part here, then the limits, and then plus again the same thing, and we have differentiated now this one n minus 1 1 minus x power n minus 2, and this minus x. So, that will be minus 1 again the differentiation, but that minus 1 has been taken care because in this formula here minus sign should appear. So, we have this because this first integral, this will disappear when x approaches to 1, this integral will become 0 when n is a positive integer. So, that means 1, 2, 3. So, in that case we have this will become 0, and when x approaches to 0, because of this x, this will become 0. So, when n is 1, what will happen? So, for n is equal to 1, this will be anyway, we can deal it separately, we do not have to consider that case in this way. So, this is naturally when n is greater than equal to 1, because when n is equal to 1. So, we do not have this term, and we can evaluate this easily for the given function x power m minus 1. So, here we do this again, this partial this integration by parts several times until we can remove this exponent here, this power n minus 2. So, depending on n, we have to integrate several times. So, in general what we will get here, we will keep on doing this. So, we have n minus 1, in the next iteration we will get n minus 2 and then n minus 3 and so on, until we see that this n is becoming here the 1, and then this disappears. So, the n minus n. So, this when 2 was there, we got 1 here, and when n will be coming at some point of time. So, n minus 1 will be coming here. So, in that case this will become now n minus n, and then same thing will happen here. So, we have m, and then in the next iteration this will be m plus 1, then m plus 2 and so on, and we will we can see the pattern here. So, when 2 was there, the 1 is coming in this term, the 3, then 2 will come and so on. So, 1 less is we are adding here. So, we have n minus 1. So, n minus 2 will be coming here with m. So, we have in the denominator these terms m plus 1 up to m plus n minus 2, and in the numerator this is going up to 1. So, this here n gets cancelled with n, and this is the 1 term. So, this is nothing but the n minus 1, n minus 2, and this product continues up to 1, and then this integral becomes 0 to 1 and x power. So, because here the power is increasing, here it was x m minus 1, after integration once by part we got this m here. So, naturally this is same as what we have in the denominator, the last term. So, this power here of this x will become m plus n minus 2. So, m plus n minus 2 dx, and now this is the integral with no other term, 1 minus x term disappeared completely. So, we have only one term in the integral, and this is easy to integrate. So, what we get after this integration, this will be x power m plus n and minus 1, because we will add 1, and then this will be divided by again with this term, and then we have the limit 0 to 1. So, when we put this x is equal to 1, we will get 1 over m plus n minus 1, and that is the reason we have taken here this product to m plus n minus 1. That is the that is the next term when we add 1 there. So, we have the continuity here, we have m plus 1 up to this m plus n minus 2, and then the last term m plus n minus 1, and when we put 0 there. So, this will be 0. So, this is the outcome here out of this integral. Out of this integral we will get just 1 over m plus n minus 1. So, this term here we have incorporated. So, m plus n minus 1, and the numerator here, because this was the product from n minus 1 to 1, and that is the definition of the factorial we use. So, this is the notation now, factorial n minus 1 we have used for this product n minus 1, n minus 2 up to 1. So, this beta m n, when this n is a positive integer, we got that this is factorial n minus 1, and then here this product m plus 1 up to m plus n minus 1. So, same thing we can do when we assume this m to be positive, and noting that this beta is a symmetric function which we have just seen before. So, there is absolutely no issues, we will get the similar formula, this m will be replaced by n. So, in this case we have just seen when we have taken n a positive number. So, when we have taken n a positive integer, we got this beta m n as factorial n minus 1 and this product of these m terms, and we can do the similar calculations when m is a positive integer, and in that case also we will get a similar result, and the result will be just we can replace this m by n, we will get this expression here with m minus 1 factorial, and then these terms with n plus 1 and the same term m plus n minus 1. If both are integers, m and n both are integers, so in this case we can either take this case for example. So, when here m is also integer, so that means we have m plus 1 and so on, this product again appearing of these integers with a difference of 1. So, if we multiply in the numerator in the denominator term also m minus 1, m minus 2 and up to 1. So, basically this side here. So, what we are getting that 1, 2, 3 and so on m minus 1 m, and this product goes up to m plus n minus 1. So, here also this was nothing but the factorial m minus 1. So, this was factorial m minus 1 term. So, we have multiplied here with factorial m minus 1 term, and then this also becomes from 1 to m plus n minus 1 the product. So, this is becoming again the factorial m plus n minus 1. So, we have m minus 1 there and factorial n minus 1, and in the denominator here we will get m plus n minus 1 factorial. Same thing we can observe if we take this formula for example, and in this case we have to multiply by this n minus 1 factorial, because we have to now multiply here also by n minus 1 factorial, that means 1, 2 and so on, and n minus 1, and then we have n. So, this continues now to this one, and this will again become this factorial m plus n minus 1, which is considered here m plus n minus 1 factorial. So, this is the formula when m and n both are integers. So, we have this beta function can be written in terms of the factorial. So, factorial m minus 1 factorial n minus 1 and divided by factorial m plus n minus 1. Now, evaluation of the gamma function. So, again we have this integral 0 to infinity e power minus x power n dx, and we will use the same idea that just integrating by parts we will get a nice relation of this gamma or n plus 1. So, when we integrate by parts, so naturally now we will differentiate this x power n minus 1. So, we have e power minus x, the integral of e power minus x will be same minus e power minus x, x power n will remain as it is, and then we have this limit here 0 to infinity. So, limit 0 to infinity plus integral. So, that minus will become plus here. So, integral, and then this integral of this e power minus x, which is minus e power minus x, and that minus has been already taken care. X power n minus 1, when we differentiate this, we will get n x power n minus 1. So, this first term, when x approaching to infinity, because of this exponential, this will go to 0, and when x approaching to 0, because of this x, n is positive, because otherwise this does not make sense. We have already seen the convergence. So, this will become 0, the first term. So, what do we get now out of this relation, that this gamma n plus 1 is equal to, so this here, if we take this n outside the integral, so this integral is nothing but n, and then we have 0 to infinity x power n minus 1 e power minus x dx. And as per the definition of the gamma function, what are we getting? Just n is replaced by n minus 1. So, that means this here, this integral is nothing but gamma n. So, we got this relation that gamma n plus 1 is equal to n gamma n, and that is a very useful relation which will be used to evaluate this gamma functions. If n is a positive integer, what will happen? So, when n is a positive integer, this we can easily evaluate in this case, because as per the definition or as per this recurrence relation, what do we get? Gamma n we can write down in terms of, like, gamma n will be n minus 1 gamma n minus 1. So, here if I use here gamma n and we use this relation, so this will be n minus 1 and gamma n minus 1. Again, for gamma n minus 1 we can use that relation. So, we have n minus 1 and this is n minus 1 and gamma n minus 2, and we can keep on repeating this. So, n minus 2 gamma n minus 2. So, n minus 2, then here n minus 3 gamma n minus 3. So, this we will continue until we get this 2 1 and then gamma 1. So, at some point we will get like gamma 2 there, then which we can write 1 gamma 1 and so on. So, we will get this when n is a positive integer. The simplification we will get that the gamma 1 we can easily compute now, and we will end up with, because this was a positive integer and we are just reducing by 1. So, we will end up with this gamma 1 naturally. So, this gamma 1, if we see from this integral, so when we substitute there n is equal to 0, if we substitute here n is equal to 0 in the integral, we have gamma 1. So, n is equal to 0 means this term will disappear. So, we have simply the integral 0 to infinity e power minus x dx, that is the gamma 1, and this integral we can evaluate easily, because exponential minus x, the integral is minus exponential x, and we have the limit here 0 to infinity. So, when x approaches to infinity, we will get this 0, and minus plus x approaching to 0, we will get 1. So, this will be 1. So, the value of this gamma 1 is 1. So, having this value now, so we have gamma n is equal to 1, 2, 3, the product up to n minus 1, which in terms of factorial we can write down. That means gamma n is nothing but the factorial n minus 1. So, that is a nice relation we got, that such an integral which was improper integral, but we have a nice relation in terms of the this factorial when n is integer, at least in this simple case. So, the gamma n is coming to be n minus 1. Now, moving next, we have another nice relation, not only for the integer, but also for this half, at least gamma half, which is going to be again useful. So, if we have that recurrence relation gamma n plus 1 is equal to n gamma n. So, for some non-integer number as well, we can compute using that recurrence relation, and at the end, when if we end up with this gamma half, then certainly we can get the value. So, this will be again helpful. So, gamma half is square root pi, which we can observe by the definition. So, gamma n is 0 to infinity e power minus x and x power n minus 1 dx. So, if we substitute this, x is equal to y square in this integral. If we substitute x is equal to y square, this will have another form of this gamma integral. So, what will happen for the substitution? The dx will become 2y dy. The limits will remain the same. So, we will have 0 to infinity e power minus y square, and this x will be y square. So, y 2n and then minus 2, but dx is again 2y dy. So, this y, so this 2 times 0 to infinity e power minus y square, and we have y power 2n minus 1 and dy. So, this is another form of this gamma integral which we will use now. So, this is 2 times 0 to infinity e power minus y square y power 2n minus 1 dy, and now we will substitute for this n as n is equal to half. So, having this, we have 2 times 0 to infinity this y power, when n is half. So, this becomes 0. So, y power 0 1. So, we have e power minus y square dy, and this is a well known integral which we will also evaluate in when we will be talking about the double integral later on. But this one, the value of this integral 0 to infinity e power minus y square and this dy, in fact, we will see later that value of this minus infinity to plus infinity e power minus y square comes to be square root pi. So, at present we will assume this, but it is very useful integral, and better to also remember this value square root pi. And having this one, now we can evaluate this. So, 2 times, and the value of this integral is coming to be square root pi by 2, because this is in the half range, not from minus infinity to infinity, but it is 0 to infinity. So, this is 2 times and the square root pi by 2, and this 2 gets cancelled, and then we have the value is square root pi. So, gamma half is square root pi, but provided we have just without evaluation we have used this value, but after few lectures we will evaluate this when discussing the double integrals. So, this for later. And now, we have also several different forms, like we have seen just for the gamma function by some substitution we got another form. Same thing happened for beta functions. So, let us just go through some forms that could be useful to evaluate the integrals or to recognize the integrals in a different format. So, we have this standard definition of the beta m n, and if we substitute, for example, here x is equal to 1 over 1 plus y. So, in that case your dx will become minus 1 over 1 plus y whole square and then dy. So, this will be the relation, and then this beta m n will become. So, let us talk about the limit. So, x, when x was approaching to 0 here, the y is approaching to infinity. So, this we will get this integral as this minus sign, and this will approaching to infinity. When x is approaching to 1, when x is approaching to 1, the y will approach to. So, 1 is equal to 1 over 1 plus y, that means the 1 plus y is equal to 1. So, y is 0. So, y will approach to 0, and then we have this minus sign. So, which will revert the limits. So, we have 0 to infinity there, and so 0 to infinity, and then we have this x is replaced by 1 over 1 plus y. So, we will have here 1 over 1 plus y power m minus 1, 1 minus x. So, here from here we can also get this 1 minus x. So, what will be 1 minus x? 1 minus x. So, 1 minus x will be 1 minus 1 over 1 plus y, and this is 1 plus y minus 1 over 1 plus y. So, this will be y over 1 plus y. So, here y power n minus 1, which is exactly here, and this 1 plus y power n minus 1. So, combining those powers now, so here we have this m minus 1 power, and then here we have n minus 1 power. So, we will have m plus n and minus 2, but this 1 plus y power 2 here will get cancelled with those 2 here. So, we will get this power m plus n. So, this is another form of the beta function given here, y power n minus 1 and 1 plus y power m plus 1. And we should note that with this substitution the integral limits changed completely. So, in the original integral it was 0 to 1, but this is also the same function, but having this 0 to infinity now into the picture. Or we can, because this is a symmetric function, so m n we can replace m by n and n by n, the value will not differ. So, we have y power here m minus 1 and 1 plus x power m plus n. So, this integral or this integral, they are the same, having the same value as beta m n. We can get another form when we substitute this x is equal to sine square theta. So, having this x is equal to sine square theta. So, again this will become sine square 2 m minus 1, this will be 1 minus sine square theta. So, that will be cos square theta. So, here we will have this cos square theta power n minus 1, here we will have sine square theta power m minus 1, and then the dx will become 2 sine theta, and sine theta will become cos theta and d theta, and then the limit. So, limits when x is 0, so theta will be also 0, when 1, so this will be pi by 2. So, we are getting here now this is 2 times and then sine power. So, 2 m minus 1. So, this was square. So, 2 m minus 2, but one sign is there. So, we have 2 m minus 1, and then same thing here for cos power 2 n minus 1 d theta. So, this is the one another form of this beta m n in terms of the trigonometric functions. So, beta m n is coming to be 2 and 0 to pi sine 2 m minus 1 cos 2 n minus 1 d theta, or by just changing the role of this m and n, we can also get this sine 2 n minus 1 theta and cos 2 m minus 1 theta. And now we can also look for some different forms of the gamma functions, which is e power minus x, x power n minus 1, and in this case if we substitute this x is equal to lambda y. So, x is equal to lambda y, the limits will remain the same, and we have a slightly different form. So, this lambda n minus 1 will come out from this term, and basically we have this integral 0 to infinity e power minus lambda y, y power n minus 1 dy is gamma n over lambda n. Also, if we substitute this e power minus x is equal to t, so we will have again very different form, because from here now we get 1 over t is e power x. So, we get x as ln 1 over t. So, e power minus x is replaced by t, and then x will be replaced by ln 1 over t power n minus 1. So, this e power minus x with this dx will become this dt. So, there will be no extra term will be coming here, and then we have gamma n as minus 1 to 0, which will be again replaced by 0 to 1. So, this is another form of this gamma function, and in terms of this integral, that such integral can be just written as gamma n. So, the relation between this gamma and beta function, we know that when m n both are integers, we have seen this relation that beta m n is can be written as the factorial m minus 1, factorial n minus 1 and m plus n minus 1 factorial. In terms of the gamma function, because we have seen that relation that this gamma m is nothing but the factorial m minus 1 and gamma n is nothing but the factorial n minus 1, gamma m plus n will be factorial m plus n minus 1. And what is interesting, which we are not showing here, that this result which at the end here, this result also holds when this m and n are not integer. So, they are just a positive number. In that case also this results hold, because this gamma is defined for non integer values as well naturally. So, this beta m n is defined as gamma m gamma n over gamma m plus n. Just an example to so if we have this integral which we want to evaluate 0 to 1 x power 4 1 minus x power 5 dx, we know the definition of the beta function. So, sometimes difficult to recognize, but in this case it is not so difficult. So, we by some substitution we can easily convert into this form and then we can evaluate. So, for instance, in this case if we take this square root x as t. So, if we have taken here square root x as t. So, this will be 1 minus t, which we want to have to see this beta form. So, that means this x is equal to t square we can write. So, this will become t power 8 and this is 1 minus t power 5 and dx will become 2 t dt. So, this t power 9 and 1 minus t power 5 dt. So, this is exactly the integral we were talking about in this beta. So, we can write down this as the beta. So, here we have m minus 1, that is 9, that means we have 10. So, here 6. So, this is beta 10 6. So, this is 2 times and this beta function, the arguments 10 and the 6, which we can evaluate now. These are the integers here. So, gamma 10, gamma 6 and gamma 16, the sum of this by the formula just shown before, and these gammas we can evaluate. So, this is factorial 9, this is factorial 5 and this is factorial 15, and again we can simplify this and this will be the number coming 1 over 15015. So, we can evaluate several such integrals with the help of this beta function. So, the conclusion is that we have seen these two definitions of the beta function and how to evaluate these functions, and mainly the interesting was that the gamma half we have computed it is square root pi, and also this relation is very useful between beta and the gamma function. So, beta m n is gamma n over gamma m plus n. So, these are the references used, and thank you very much.